My name is Anya. I'm very excited to present our paper, When is Heterogeneity Actionable for Targeting? This is joint work with Ron, who's sitting over there. So everybody in this session is talking about how to run experiments properly. And I'm actually going to talk about what happens after you're done running the experiment. And one possibility that you can do after running an A/B test is to see what kind of people tend to respond better to what kind of interventions. And then use the results of your experiment to assign different people based on their characteristics to different interventions, which we will be calling targeting or personalization. And I think intuitively, at least for us, we had this feeling that the more interventions you implemented in the first place, the easier for you would be to get a high value from personalization. Because instead of for each person just assigning one of the two interventions, now you can choose for each person 1 out of 20. And in this paper, we are answering a few questions. First, is heterogeneity in responses enough for targeting? Because sometimes it seems like, oh yeah, we're doing all this heterogeneous treatment effects estimation, and then we kind of implicitly assume that the reason we are doing this exercise is that maybe potentially later we can do personalization. So is the link between heterogeneity and personalization as clear as it seems? And especially, is it really true that when you have more interventions, you would have bigger returns to personalization? Let me start with describing the empirical context that we are going to think about. So we have data from 2 experiments for flu shots vaccinations. Both were run by Katie Milkman. And what happens in both, there were a lot of people. They were getting text messages with different interventions that were behaviorally informed. I'm going to show you some examples in the next slide. And in the Walmart study, these were the Walmart customers who got the message that you can actually get your flu shot at Walmart. And for the Van Geisinger study, which had a lower sample size, but still huge, these were the people with an upcoming appointment at a physician. And they got the message that along with your physician appointment, you can also get a flu shot. I will just say here that both of those were one-shot experiments, so we're not thinking about sequential or bandit stuff. It's just like we ran an experiment and now we're going to personalize. So here are some examples of, this is the figure from the original paper of the Walmart study. Here you can hopefully see some of the messages, but the best performing one was flu shot is waiting for you with 2 texts 3 days apart. And there were some other ones, like you can protect others by getting a flu shot, or you can protect yourself. And presumably, these messages can work differently for different groups of people, depending on their characteristics. The blue line here is the control, so no message. And all these other messages are behaviorally informed interventions. In these original papers, they just compare the average treatment effects, and we are going to be doing the personalization exercise. Here's a similar figure for the Van Geisinger study. They have slightly different messages. And as you can see here, the confidence intervals are slightly larger because of this sample size that is smaller. So now what do we actually mean by personalization? So let's start with the simplest way of personalization, which is not to personalize at all. And this would be our benchmark. We would call it best uniform policy. So like that example that I showed you, flu shot reserved for you with 3 days apart would be our best uniform policy, because if we apply it to everyone, we are going to get on average the highest possible rate of vaccinations. But now let's do the cool stuff. Let's actually personalize. The easiest way to do that would be to run a regression, where we regress our outcomes, that is whether a person got a flu shot or not, on the intervention that they got, and also their characteristics. and most importantly, on the interaction between the characteristics and the intervention. And what is going to happen, let's look at these two icons at the bottom of the slide. So let's see that the left one is Ron. He's a famous scientist, and when we run OLS, it would say that Ron would actually respond very well to the statistics about flu. And we think that for him, this would be the most important intervention. The other ones, for example, let's say the second one is sharing a video, not so much. Here, this is me. I'm a Gen Z for PhD students. I don't care about statistics, but I care about videos on Instagram. And maybe for me, the second intervention, according to our predictive model, would be the most effective. Of course, OLS is very, very restrictive, so we can just replace it with a machine learning model. But retain the idea. We are going to predict the outcomes based on the characteristics of the people and the interventions that they received. This is called predict and optimize. There are also other ways of doing personalization exercise. One of them is using causal forest, which is a recent method developed by Susan Athey and co-authors. There, the idea is to look for heterogeneous treatment effects as opposed to just the outcomes. And finally, there is policy tree, which is an extremely recent paper. That one just directly looks for a targeting policy. So what we did as our first step, we applied all of these methods to our two data sets. So here for the best uniform, that's the thing that I described. What happens if we assign everybody to the same policy, but this policy would be the best that we could get. So this is the percentage of people that would get vaccinated, 31.2 in the Walmart case and 31.5 in the Van Dyson case. Now, what are the numbers on the right side of the table? This is our counterfactual estimation of what would have happened if we were to use the personalized policy of each of the 5 methods. We estimate this using holdout sample with IPW. And what I want you to look at is the difference between the first group of numbers, which is Walmart, and the second group of numbers, which is Van Geisinger. And as we can see, Van Geisinger has a much more substantial returns to personalization, while the context was actually somehow similar in both. And so we were very interested to see what exactly is happening here. We had a few hypotheses. Could it be that we have not enough relevant covariates in one or the other? So actually, Van Geisinger has more covariates. But also, if we just run OLS for both of these studies, we find significant interactions with some of the covariates. So there is heterogeneity, and the covariates are actually meaningful for both of the studies. Could it be that the sample size per arm is doing something sketchy? Well, actually, Walmart has a higher sample size per arm. And in that case, probably it would be more accurate in estimating the predicted responses. And so it should have higher returns for targeting, which is not the case. Could it be that methods are somehow not great? Well, we did 5 of them. So our answer to what is happening with personalization is that even though both of them have heterogeneity, not all of the heterogeneity is good for targeting. And we would call the heterogeneity that is good for targeting actionable heterogeneity. People told us not to use the term useless heterogeneity. And we find that the amount of this actionable heterogeneity would depend on 3 forces: within treatment heterogeneity, cross-treatment heterogeneity, and cross-treatment correlation. I'm going to explain what it means in a couple of slides. First, let's see what is actionable heterogeneity. So the titles here from the old paper, still useless. So on the left panel, what you can see is you can see heterogeneity. If you so there are 2 responses. Response of people, let's say example covariate is age with different age to treatment A and treatment B. And let's say we have sales on the y-axis. If we were to run a regression of sales onto age and the treatment and the interaction of age and treatment, what would be the coefficient of interaction? It would be something significant. because we see that the slopes are different. We have like a classic example of moderation of the effect. But this heterogeneity is not good for targeting. Why? Because everybody should still be assigned to treatment B. Even though the effect diminishes for people with higher age, it doesn't mean that we should start assigning somebody to treatment B. However, on the right panel, we see that there is this crossover. And this crossover means that people with low age should be assigned to treatment B, but now people with higher age should be assigned to treatment A. And so we are going to look for the presence of these crossovers in heterogeneity. When we have more than 2 arms, not all crossovers are good. Again, on the left panel, we see there is a crossover, but actually there is also this blue treatment C that works just much better than either of the two. And again, we should be assigning everybody to treatment C. The good crossover is on the right panel. So somehow we need to beat the best arm, which appeared a few times before as our benchmark. And again, we see that this is. So now let's see what is the role of different moments of the data or different forces in the data on this actionable heterogeneity. So let's start with within treatment heterogeneity. This is just like when we fix one intervention and we look at the responses of all people within that intervention. How different are they? And the more different they are, the more useful heterogeneity we are going to have. So that's one force. The second force is the independence or cross-correlation across treatments. So what can happen is that everybody likes videos and everybody just responds better to them. Or maybe there is more independence across treatments and less cross-correlation. In that case, some people are going to like one thing, other people are going to like the other thing. In that case, again, we are going to have more useful heterogeneity. Finally, the third important factor is the variation across treatments. So now if we aggregate all treatments to the average treatment effects, and we see how much of the variability is there, we will see that if there is a lot of variability, it's not going to be good for our targeting purposes, because like this best arm would be so high that it would be hard to beat. This is what happens on the left panel, on the right panel. It's all. Okay, so now actually we went back to our 2 data sets and we computed these 3.
Actually, I think on this third one, I'm not totally sure.
Okay.
I got the definition that you're going for. When you say cross heterogeneity,
Yeah.
what specifically is that referring to? Is it just the dynamic range between the alternatives?
It's the average treatment of the average responses. So each arm has an average response.
Okay, got it. And it's
and
just
then the variation.
yeah, it's the dynamic. Okay.
So we went back to our data sets, we computed these 3 moments. What we found is that for within treatment heterogeneity, Penn-Geisinger was better than Walmart. For cross-treatment correlation, actually Walmart was better than Penn-Geisinger. It had more independent treatments. And for this one, they had pretty much the same variation of the cross-treatment heterogeneity. So what do we do with that? Well, thanks to our reviewers, we combined them finally into a pretty good model in my mind. And we solved this model analytically for 2 arms. And numerically, we do this for many arms. And what is cool about these numerical models is that you can use it when you have priors of these 3 forces before running an experiment. So like you have an approximate idea of what is going to be your within treatment heterogeneity, cross-treatment correlation, and cross-treatment heterogeneity, and you can estimate the amount of personalization value that you might be getting by, the idea is very simple. We're using normal distributions, and we're drawing from normal distributions, and then we literally compute the targeting value on this simulated data. One interesting thing that we found is that if the underlying distribution of these main effects, so the average responses to arms, is not normal, but instead it's something more peaked, like a spike and slap, more treatments can actually hurt the value of personalization. and 20 treatments might work worse than 2. I'm happy to talk about this more offline if people are interested, or you can read the paper. And the good thing is that this model can be used either before when you have priors or after running an experiment to see what was the amount of your actual heterogeneity. This is the application of this model to our 2 data sets. So this model also includes the estimation error because we never have access to true potential outcomes. And we always somehow estimate them with noise. We have to add back this noise into the estimation. And when we do that, so these dots represent the estimated value of personalization using our model, and the dotted lines are the value of personalization that we are getting by applying methods. So again, these solid lines, just simulation, just normal distributions with 4 parameters. Finally, in conclusion, not all heterogeneity is good for targeting. Only the heterogeneity that results in crossovers with the best uniform arm is useful for personalization. It is determined by 3 moments of the data: within treatment heterogeneity, cross-treatment correlation, and cross-treatment heterogeneity. And more arms do not necessarily mean more successful personalization. Thank you so much for your attention. Here's the paper. Be happy to take questions if I have time.
We have plenty of time, like for 3-4 questions.
Yes, I actually just wanted to ask you about what happens with multiple covariates. So isn't it possible that you could have the same, the same treatment exhibiting low, let's say, cross-treatment correlation, high cross-treatment correlation, depending on which covariate you're looking at?
Absolutely, absolutely.
So the follow-up for that was on in the differences in the data sets, because there were I think, weren't there 20 covariates in this? I'm curious if you were able to extract what were the useful covariates using that kind of analysis.
Yeah, so in the graphs that I showed, the figures that were obviously stylized.
Yeah.
But so what we do in the actual paper, we use XGBoost to group people's by quantiles of the predicted response. So this summarizes the covariates, and we're looking at the variability along these summarized covariates. And for Penn-Geisinger, actually, the most predictive covariate was the median income of the zip code.
Okay. I see, that wasn't available in the Walmart data?
It actually was.
Okay. That's interesting.
That's interesting. No, that's something that is not very obvious. Yeah. But there were other covariates that were not, I think, available. I think BMI was also predictive and I think not available in the Walmart. It's in the paper.
That's super interesting. Yeah, thanks.